This is Unit 9 Probability, Day 2, Independent and Dependent Events. Just kind of outlining what makes events independent is that if the two events occur and one event does not impact the probability of the second event. Meanwhile, if the events are dependent events, if when one event occurs, it in some way changes the probability that the second event occurs. Okay, so right here on the first example, a die is rolled and then a second die is rolled. So whatever happens with this first die, that's not going to impact the probabilities on the second die. They're not tied together in any way. So you're actually going to have this be independent right here. And on the second one, a card is selected from a deck of cards and not put back. Then a second card is selected. So because this first card is not put back, that's going to at least impact the denominator of the probability for this second one. So if a standard deck is 52 cards, now the second card, there's only 51 cards if the first card was not put back. This is an example of dependent events. On day one, we were doing conditional probability. Every single one of those were dependent. So now we're going to see independent and dependent together. This isn't really an example for your notes, but I did like it showing the sample space for an experiment, saying that if a coin is tossed, you could have heads or tails. And you can see where heads are, these three, and tails. And you can see that that accounts for 50-50 chance of heads or tail. Then the spinner is also spun, so you might land blue, red, or green. So here's blue, but you'll also see that there's a blue here because maybe you did heads on the first coin flip or tails. And so blue has to occur twice. Same for red, same for green. So there's actually 6 total possible outcomes. So the probability of getting heads and green is 1 out of 6, for instance. I just like this because seeing how they write sample spaces, also seeing how you can do the same probability can be found by multiplying the probabilities of each sample event. And that is what leads into this box of notes, that to find the probability of two events when they are independent, you multiply them. So like where I said 1 out of 6, because there was 6 total, we could have done 1/2 for heads, 1 out of 3 for green, 1/2 times 1/3 is 1/6. And that's what you're going to be seeing whenever the events are independent. So, reading through this, you're going to have red, green, and yellow marbles. Girl draws a marble, not liking the outcome, she puts it back, which I find a bit of ridiculous, but whatever. Draws a second time. So this is with replacement. On example 1, part B, there was no replacement. This is with replacement. So since this is with replacement, this makes the two events independent of one another because she kind of resets for the next one to happen. So for the first draw, what you're going to have is that we're finding the chances of her getting red on both draws. So there are 4 red marbles out of 15 total. So 4 out of 15. And what we're going to do is we're going to multiply that with the probability of the second event happening. And that second event is also drawing a red marble. Since she replaced it, there are still 4 red marbles and 15 total. And 4 over 15 times 4 over 15 will give me my answer. So I get 16 out of 225. And as you've seen by now, I like to use a percent response. So 16 out of 225 gives me 7.1%. So she didn't like it, but then she got it again. All right, so that's how it works whenever it's independent with replacement. Okay, now we're going to look at a probability of 2 dependent events. What's going to happen here is you're going to see this formula from yesterday. This was the conditional probability. We're going to have 2 dependent events. There are going to be 2 simple events here that we're going to have to calculate the probabilities for. We will still multiply them. Let's go ahead and take a look at an example here. It's the same setup as far as the marbles go on the previous problem. Graham, it says, draws a marble and does not put his marble back in the bag. That makes this event dependent for the next one, because by him not putting his marble back, it changes the probabilities for the next draw. His friend draws a marble. What is the probability they both draw green marbles? So let's go ahead and take care of Graham. And for him to get a green marble, there are 6 green marbles out of 15 total. Now, according to my formula that was in the blue box that we just took notes on, I'm going to multiply that with what his friend gets. Now, his friend's probability has been impacted by Graham's action. So for his friend to get a green marble as well means that Graham has already gotten a green marble. There's no longer 6 green marbles, there are only 5. Also, there are only 14 marbles now in the bag. So we're going to multiply this out. 6 times 5 is 30. 15 times 14 gives me 210. So 30 out of 210. You can reduce that if you want to, but I'm just going to provide a percent answer, so 14.3%. This is more or less just a review from yesterday, but I'm going to hit a couple different components that you might not have thought about. It says students who draw odd numbers will be on the red team. Students who draw even numbers will be on the blue team. If Monica is on the blue team, what's the probability she drew the number 10? So this is conditional probability. We're given that she's on the blue team. With that said, my sample space is much smaller than just all the numbers from 1 to 20. They're actually only the even numbers, which in total, there are 10 of those from 1 to 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And the number 10 is only one of those, so 1 out of 10, or 10%. So if you're given that she's on the blue team, there's a 10% chance that she got the number 10, or any particular number that's even. But using the same situation and setup, let's take a look at this. Same situation. If Monica is on the blue team, what's the probability that she drew the number 11? Well, referring back to the sample space I just sketched out there, the number 11 isn't there. It occurs 0 times. That means there's a 0% chance she drew the number 11. Because if she's on the blue team, she drew an even number. She can't draw the number 11, so 0%. This last one is another little bit of an interesting situation. So if Monica drew a 10, what's the probability that she's on the blue team? So if the 10 does happen, what are the possible outcomes for teams for her to be on? Well, since it's an even number, she has to be on the blue team. So there's only one possible outcome. So for that to happen means it's a guarantee. And guarantees and probability means it's 100% for sure going to happen. So just keeping an eye on when 0% happens and when 100% happens. All right, that wraps up day 2. Very short lesson. None of these are going to be crazy long. Let me know what questions you got. Thank you very much. I did forget to mention that on the homework for number 24, that is a challenging problem. That's one I want you to spend probably about 5 to 10 minutes thinking about, see if you can come up with an idea. I am going to tell you that I use a little bit of basic algebra to set that one up, thinking about what the formula says, and using the variable n. And assume that every object is unique in it, that there's not duplicates of the objects. That'll simplify it down as far as what to do